Hello YouTube! Today we're going to be talking about the moment of inertia. This is also called angular inertia sometimes. This is pretty much just how hard it is to spin an object, or in particular how hard it is to make it change how it's spinning. There's going to be a lot of calculus, so buckle up. In particular, hi. There's also a cat. In particular, ideally, end of the day, you should be able to do the integral calculus for rotational inertia to derive it for a given object. The big step for that is going to be representing dm in terms of, as in the infinitesimally small chunk of mass, in terms of the volume of the object, and using that to replace dm with dr. From there, it's just the standard integrals, but you should also be able to do it for point masses, so in discrete functions, but then also in continuous functions as well. So to get there, we're first off going to start by talking about why this is a mathematically useful concept, and to do that, we're actually going to derive the kinetic energy equation for a rotating object. So popping over to paper for that one, because it's a bit much to write on the screen with a mouse. Alright, so let's say we've got kinetic energy, and hopefully you're pretty familiar with that by now. Your kinetic energy for a given object will be 1/2 mass times its velocity squared. And that'll also be true for every little piece of the object. So if it's spinning, if we take the summation of all of those kinetic energies from all of those tiny little objects that make up our sort of macro rotating object, that'll tell us how much kinetic energy is stored up in the fact that the thing is moving in a circle. So that's our goal. If we think of this as a slightly different way, what we can say is that our velocity squared our tangential velocity for the spinning object for any given little piece of that object is going to be equal to r times r omega. And so if I plug that in here, what I'll get is a summation of 1/2 m for each little chunk r omega squared. And if I pull out the things that remain constant, what we'll wind up with is a 1/2 in the beginning, the summation of m times how far away that mass is from the center, squared, and then that summation is times the omega squared because the object rotates at a fixed rate. It's not like the outside of the object is spinning through a greater number of degrees each second, even though it's moving a greater distance. And that's why we sort of say that our velocity is equal to r times omega. Okay. So, what's special about this little thing in here is that this is actually pretty much similar to 1/2 mv squared. I mean, that's where we started, so that makes sense. But there's this mr squared quantity here. And so people gave this thing a special name. And it's going to keep popping up everywhere. But this is our moment of inertia. And so what is moment of inertia? Turns out it is kind of the equivalent of mass, but for spinning. When you have a moment of inertia, it's a measurement of how difficult it is to cause an angular acceleration of an object instead of a measurement of how difficult it is to cause a linear acceleration for just normal inertia. More mass does mean that it is harder to cause it to spin because it's harder to change what it's doing at all. So yeah, of course it's also going to be harder to do what it's doing from spinning. The one that's weird is if you've got more mass further away from the center, it's also harder to cause the angular acceleration. And you can get some pretty easy evidence of this on your own. It helps if I swap to the PowerPoint that I'm talking about. You can get some pretty easy evidence of this on your own. Sorry, I was trying to move the camera and just move the PowerPoint. If you do something like pick up a chair. So if you pick up the chair and you try to shake it back and forth from the middle, it is much, much easier than if you pick up a chair and try to shake it back and forth from the ends. And the reason for that is that the greater proportion of the chair's mass is located away from my hands when I'm trying to shake it by the end, whereas a greater proportion of the chair's mass is located near the pivot point at the center when I'm trying to shake it from the center. And so it gets harder to shake, it gets harder to change how it's spinning when more of the mass is located further away from the point that it's spinning around. What that means is the shape really, really matters, and that squared is where that sort of comes in. As a result, different shapes wind up having different scaling factors that get popped in front of the mr squared when you're actually calculating the moment of inertia for that shape. We'll literally be deriving what those scaling factors are, but that's sort of the main way you'll interact with them unless the problem is explicitly saying derive the shapes equation. So generally speaking, the more mass there is, the further from the center of the object, the harder the thing is for it to spin. This next one bothered the crap out of me for a really long time, but you have to think of it in the actual correct way. So a solid sphere, where your mass is evenly distributed from the outside all the way into the middle, will be easier to spin than if you took the mass from the middle and you smushed it out to the edges so that you made a hollow sphere of the same mass. And that last part's important. So obviously, if you hollow out a solid sphere, you'll get it with a easier to spin properties because you've just taken the same thing minus stuff, and less stuff is easier to spin. So for this to be a useful statement, you do have to like take it and push it towards the outside. And that for me was always this weird sticking point where I was like, no, a hollow sphere should be easier to spin and will be easier to spin than a solid sphere. And it is unless they're of the same mass. So the actual equation for this, obviously our life has to be hard. So if we take that old situation that we had before, that only works for discrete objects. So if you have a point mass, the moment of inertia, which has the letter capital I, for a point mass is equal to mr squared, where m is the mass of the point mass and r is the distance away from a center. If you take any number of discrete objects where you know what their moment of inertia is, you can add them together to get the total moment of inertia of a full object made of a composite of them. So you can just take a summation and that's great. The problem is for continuous objects, you are of course doing calculus, so the moment of inertia for an object will be equal to the integral of r squared dm across the mass of the entire object. So you're taking each little tiny piece of mass, you're multiplying it by how far away it is from the pivot point squared, and then that'll be your thing. We'll come back to another equation in a sec, but for now this is a really great starting point. So we're going to do some examples. First one, derive the center of mass and moment of inertia for a uniform rod of mass m and length L if it's rotating about its center of mass. So to start with, we better figure out where the center of mass is. Now, we've done this, and honestly, it's hopefully fairly intuitive that the center of mass for a uniformly rod is going to be the center of the uniform rod. But still just sort of going through it to see how there's slight differences between this and integral of r dm. So r squared dm versus r dm, because that's sort of our last thing we were doing like this. So for our center of mass, that'll be the integral of r dm. And for a moment of inertia, that'll be our integral of r squared dm. And this one, we get to pick our arbitrary 0 point. For this one, 0 is not arbitrary. 0 is going to be on the pivot point that we are trying to spin around. And that's going to potentially matter more later. Our specific problem, though, is that we've got a thing, it's got a mass of m, it's got a length of L, it's a rod, it's uniform. Let's dive in. So center of mass, I'm just going to pick my 0 point as all the way over on the left. And so if I do that, what I'll be doing is x center of mass is equal to the integral of r dm, but I need to figure out what dm is. Now dm is going to be my infinitesimally small chunk of mass. Well, how big is an infinitesimally small chunk of mass? Well, if I take the mass of the whole thing and I divide it by the length of the whole thing, that will need to equal the mass of a tiny chunk divided by the size of a tiny chunk. And if I rearrange that, that means that a tiny chunk will be equal to the mass of the whole thing divided by the length of the whole thing times a tiny piece of the whole thing to give us just the mass. And multiplying each side by dr to do that. Great. So I can take this and plug it back in up here. And when I do that, I'll get that my center of mass is equal to the integral of r m over L dr. And I need to integrate this from one end of the rod at an x position of 0 all the way to the other end of the rod at an x position of L. Integral of r is 1/2 r squared. Our m and our L are constants, so it doesn't really matter where we stick them. Evaluating from 0 to L. Plugging in L to r squared, we'll get 1/2 L squared over L times m. The squared drops with the L on the bottom. And we've got, oh shoot, I forgot a key part of my center of mass equation, which is that it's divided by the total mass of the object. I was like, why is there mass units on a location? Because I forgot to divide by m. Anyway, 1/2 of the length away. So center of mass is in the center. Yes! That part was hopefully pretty straightforward. For the next part, we have to be a little more careful. It's explicitly asking about having the pivot on the center of mass, so I have to pick my 0 point for my x location for r to be on that pivot. So for part 2 of this, I have to pick explicitly here is r equals 0. Our distance away from the pivot is 0 when we're on the center, which is the pivot. So doing out our integral then, we'll get that our moment of inertia is equal to the integral of r squared dm. Now thankfully dm will be the same. So it'll be the integral of r squared m over L dr. And now when we're doing this, we need to go from L over 2 behind our start point, so negative, all the way up to L over 2 in front of our start point, so positive. Because the whole thing is the length of L, so we cut it in half in each direction. Doing out that integral, we'll get r to the third m over L divided by 3, evaluated, because it's to the third power, so the integral drops down to the fraction. Evaluated from negative L over 2 to L over 2. So plugging those in, we'll get L over 2, quantity to the third, times 1 over 3 times m over L, minus negative L over 2 to the third divided by 3 times m over L. 2 to the third is 8. 8 times 3 is 24. 1 over 24 plus 1 over 24 is 1 over 12, because this negative will, I should do that in the other color, this negative will drop with minus a negative. So 1 over 12, L to the third divided by L times our mass will equal our moment of inertia. So if you've got a rod and it's spinning around the center explicitly, and this only will be true for if it's spinning around the center, this will be your moment of inertia. A couple things I want to point out here. First one, you've got that 1 divided by 12. This is effectively what I was talking about with the scaling factor. There aren't any units on that, but a rod is 1/12 as difficult to spin as if all the mass was located at a point the length of the rod away from the center. And this is if you're spinning the rod around the center. That's really all that means. Something else that comes up a lot in these is just like how you've got mr squared for your center of mass equation for a point mass. For these ones, you're going to wind up with some function of the shape, be it L, be it the radius for a sphere, squared times the mass times that scaling factor again. Cool. Next example, which is just doing it again with a slightly harder shape. So first off, let's derive the moment of inertia for a thin hoop of radius L and mass m. So for this one, kind of the same deal, except we're using slightly different geometry. So we've got our hoop, we've got our mass of m, we've got our radius of L. I think I just did that so it wouldn't get confused with the R. Honestly, it probably should have been R. And we're asked to derive the moment of inertia for that, for A. For B, it'll be a disk. For C, it'll be a wheel with a rim and 3 spokes, which I just realized we don't actually have the equation to do yet. So we're going to hold off on this one and put it as part C to question 3, which will give us the equation to do this. Whoop. Anywho, let's start off with A. Well, for A, we're trying to find the moment of inertia for a hoop. Now, intuitively, there's actually a pretty quick way to do this. All of the mass is located a distance of r away from the pivot. So it's like all the mass is in a point a distance of r away from the pivot. So the moment of inertia should be the same as for a point mass a distance of r away from the pivot, mr squared. And that's intuitively what's going to be our answer. I haven't proved it, but that's probably what it's going to wind up being. So taking my integral, it is going to be r squared dm. And I just need to be careful about what my dm is. Now for this one, because I'm going in a circle, what I'm going to do is say that for any given angle, d theta, I'll get an arc length, bear with me on this, of ds, where s tends to stand for arc length. And that will have a mass of dm. Yes. And that'll be a length of L away from the center. Now the relationship between ds and theta is that if I take my angular component and I multiply it by the radius, that'll give me my linear component. So we take our arc length, we multiply it by how far away it is, that'll give us our ds. From there, what we can do is go back and do the same thing we did before. We can represent our density and say that dm divided by ds, our tiny little chunk, is going to be equal to our total density. Well, our total mass is m, but this time our total amount of stuff isn't just L, it's the entire hoop. Well, the circumference of the hoop is 2 pi times the radius, which is L. So now, when we're doing this, what we can do is take our theta and throw that up instead of ds. And so what we'll get when we plug that in is dm over L d theta is equal to m over 2 pi L. Now, why did I not just do this in terms of ds? Well, ds is weird to try to figure out what the bounds of integration are going to be. You could probably do it, but just like how dm is weird to figure out what the bounds of integration are going to be, like how do you integrate from 0 to the full mass? ds is also going to be weird. How do you integrate from one piece of the arc length to the whole thing? Whereas spinning all the way around a circle, well, all the way around a circle is 2 pi radians, so we'll just be integrating from 0 to 2 pi. Done. And so there's sort of this extra step where we have to find a way to represent it in terms of d theta so that we can actually do our integral. Doing our integral, we need to multiply each side by L d theta. Multiply each side by L d theta. And that'll get us that dm is going to be equal to our total mass divided by 2 pi times d theta. Now theta is unitless, so gladly our length dimension dropped and we didn't accidentally wind up with an extra one of those floating around because we've got L over L on the right. Taking this and plugging it back into our integral, we'll get that our moment of inertia for our hoop is going to be equal to the integral of r squared m over 2 pi d theta. Well, thankfully, r is fixed for this one. It's always a distance of L away. And so we'll be integrating from 0 all the way to 2 pi, spinning around our full circle. Our mass times our r squared, which is just L, divided by 2 pi d theta. Well, integral of d theta is theta. If we undo the derivative, we get the thing. So we're evaluating from 0 to 2 pi, m L squared theta over 2 pi. When we plug in 2 pi, we'll get m L squared 2 pi divided by 2 pi. 2 pi over 2 pi is 1, so that drops, and we just get ml squared. And that's our moment of inertia for our hoop, which again, intuitively makes sense. All your mass is a distance of L away, so it's like you've got one point mass a distance of L away. What about for a disk? Well, here's where we get into something a little trickier, where we basically want to approach this as a set of compound shapes. What we can do is, instead of thinking about it as a line, because it's now a solid two-dimensional shape for our disk, what we can think of it as is a very thin collection of hoops. Each of these hoops is going to have a mass of dm. a very tiny chunk of mass. The distance of each of these hoops, or the width of each of these hoops, is going to be infinitely small, dr. The radius of each of these hoops is going to be 2 pi r. So for any given hoop, the whole thing's size will be the combination of those two things multiplied together, because if we take it, we can basically unbend it. It is so thin that we can take it and unbend it, and we'll pretty much just get a line. Are we ignoring that the geometry doesn't quite work out between the inside and the outside when we do that? Yes. Will it matter? I hope not. So setting up our density, because again, that's sort of the hardest, really meaty part of any one time you're doing this, we'll get that dm divided by the area that we're working with, which is 2 pi r, our length for our rectangle, times our infinitely small width of our rectangle, or circumference of our hoop, will equal total mass of the hoop divided by our total circumference for our hoop, our total size for our disk, which is pi r squared. This r should be an L, because this needs to be for our whole thing. This r will be dependent on how far out we are. Now that I've got this, I can multiply each side by 2 pi r dr, 2 pi r dr. Our pi's drop. We've got two length units, r and dr, divided by length units squared, so we're going to get back to mass, so that's good units-wise. And we've got that dm is going to be equal to m times 2 r dr over L squared. And now what we can do is set up our integral. So for our disk, it's going to be equal to our integral of r squared dm. Plugging in for dm, we'll get our integral of 2m r squared times r times dr over L squared. Now looking at this thing, we need to go from the inside of the hoop all the way out to the outside. So we're going from 0 away from the center all the way out to the full distance away from the center of L. When we go ahead and do this and take our integral, we'll get our integral of r squared times r is r to the third. Integral of r to the third is r over 4 times 2 to the fourth times 2 times m divided by L squared, evaluated from 0 to L. Thankfully, math here is pretty easy. If we plug in L, we get L to the fourth over 4. The 2 and the 4 are going to cancel down to a half. And if I haven't made a crucial mistake in here, we'll get that L to the fourth divided by 2 times m over L squared is our moment of inertia. L to the fourth over L squared is equal to L squared. So we've got m L squared times a half. So anytime you have a disk, the moment of inertia for that disk will be half as much as if it was a hoop concentrated with all the mass out at the edge of the disk. So half is easy to spin. For part C, we'd have to add together a bunch of things. Literally, it's just going to be adding, but we'll do that one later. Okay, so the steps that we went through for all of those. You're setting up your equation with mr squared. Once you've set up your equation with mr squared, you're representing the density of the object by putting the total mass of the object divided by the total size of the object, be that L if it's just a rod, be that base times height if it's a rectangle, something like that. and you're using that to represent your density of your object. You use your density of your object to get dm in terms of either dr, or if it's something that's round, maybe theta, just something that you can easily integrate over, and then putting that into your integral. Once you've got that, set the bounds of integration so that they actually go from one end of the object to the other and encompass the entire thing, using your 0 point always as the center of mass for the object, which normally is just the middle of the object. So some common shapes. Okay, cool. So solid cylinders, disks, anything like that are going to be 1/2 mr squared, which we derived on our own. So go us. I just realized that I might have recorded that entire thing without. I'm going to go back and watch the video and cry if I did, but we'll find out. Hoops are mr squared. Solid spheres are 2/5 mr squared. That's one that would be worth checking out on your own. A rod is 1/12 of ml squared, which we figured out as well. A solid cylinder is going to be 1/4 of mr squared plus 1/12 of ml squared, where L is the length of the cylinder. So if you look at that, that's sort of not quite the same as a disk plus a rod, but some similarities, because there's going to be some similarities in the calculus. For a hoop about its center, like about its diameter, instead of through its center, you'll get 1/2 mr squared instead of just mr squared. And thin spherical shell, it's up there, and then the rod about the end we're actually about to prove. So the next thing that you're going to have to know is the parallel axis theorem. The parallel axis theorem is fairly straightforward. If you have a object and you're like, okay, I just figured out that my solid disk has a moment of inertia around the center of mass of 1/2 mr squared. For my, if I want to take the axis and shift it over here, the axis of rotation, the place it's spinning around, and shift it over here, I can do that, but when I do, the new moment of inertia will equal the moment of inertia for the center of mass plus ml squared. So you take the distance you've shifted it away and you add that to the moment of inertia from the center of mass. Am I double checking that that's the right equation? Who among us can say? Parallel axis theorem. Yeah, great. Normally they use H. I have never really understood why. L is my preference, but anything will matter. Anything will work as long as it's representing the distance away from the axis that you're shifting. So this is great because it means that you can really quickly find some moment of inertias. And for our next example, we're just going to quickly do the same thing that we did with the driving the moment of inertia of a rod around its center. We're going to shift it away from the center towards the edge, figure out what it'll be on the edge, and then prove that that's the same thing as if we had done the parallel axis theorem. So, doing that out, if we've got our thin rod, we've got the edge, this is at a location of 0, this is a location of L, mass of M. Our setup for our calculus is going to be very similar. R squared dm, last time we figured out that dm would be equal to dr times the mass of the thing divided by the length of the thing. And we're once again going to be integrating that, but this time we're going from one end to the other, so from 0 to L. When we do that, what we'll get is r to the third divided by 3 times m over L, evaluated from 0 to L. Well, at L, it'll just be L to the third over 3 times m over L. The third drops with the L on the bottom. 1/3 ml squared. Helps if you write a 3 instead of a 2. So that'll be our moment of inertia. Proving that with the parallel axis theorem, what we can do is we can say that our new moment of inertia will be equal to our old moment of inertia from the center of mass plus m times the length that's getting shifted squared. Well, our old moment of inertia was 1/12 ml squared. And the amount that we're shifting is by half the length to bring the pivot from the center all the way over to the end. So L over 2, and that whole thing needs to be squared. 1/12 plus 1/4 from the 2 squared is equal to 1/12 plus 3/12, which is 4/12, which is 1/3. So if you want to be able to do the same thing without having to do any calculus, there you go. You do need the center of mass 1, and you can apply the parallel axis theorem from there. Taking that 1/3 ml squared, we can go ahead and do part C of number 2, which is that if we've got this hoop with a mass of m and a radius of L, and then we've got these 3 rods that are functioning as our spokes, each of which also have a mass of m, all we have to do to find the moment of inertia of the whole thing, so the total moment of inertia, is take all our individual moments of inertia and add them together. The hoop is going to be mRL squared, because that's the formula for hoop. The rods around the end of the rod are going to be equal to 1/3, keep doing a half, ml squared. But there's 3 of them, so we just multiply it by 3. And that'll get us a total of 2 ml squared. And that's our total moment of inertia. So once you know the individual moments of inertia, you can just add them up and you're good to go. That's going to be it from me. Hopefully I don't have to re-record that. Goodbye, YouTube.